Yeah, hello, can you hear me? Thanks. Hi, so I'm Denisa. Is this working? Okay. Yeah, let me present myself a bit. So I am with Nethermind, not with INTMAX, but we work with INTMAX. So I'm a consensus researcher at Nethermind. I'm also an associate professor at the University of Bucharest, where I teach formal verification and functional programming. And that's my corner if you want to check it out. So yeah, well, okay. So today, as I said, I'm gonna speak about INTMAX2 and what we did at Nethermind with the wonderful team behind INTMAX, which is actually, we formally verified their white paper. So I will touch a bit on the formalization, which is, we are wrapping it up. But I would like to focus more on trying to sell you INTMAX and show you what a cool solution it is. And the protocol is extremely beautiful, and the white paper is just a beautiful piece of mathematics, so I invite you all to look at it. So now should I be closer to it? Yeah, okay. So now, what is INTMAX? What can it do? I think probably if you try to put it in a box, you can think of it as a based Validium rollup. But it is a scaling solution for Ethereum, and let's leave it as is, which has amazing performance. So they are claiming 5 bytes on chain, and I will try to convince you of this. The beauty part from a consensus researcher, and I will be without job probably, is that it is stateless and permissionless, so that we don't need an underlying consensus protocol. It just has to rely on the consensus protocol on DL1. I will not touch today much on the privacy using ZK proof, so I will just show the easy flow, the simplest version of the protocol, and I will just show at the end that you can use ZK proofs. Now, it is by nature censorship resistant, and it is among the fewest protocols I've seen that by design it is censorship resistant, and I will try to prove this. For the moment, they say with the current block size on Ethereum, they have a limit of 7,500 transactions per second, but there is a very nice twist here, because actually a transaction is just a batch of transactions in which a single sender can send as many transactions or tokens to a lot of other participants, right? So I will try to convince you of all these points and why they are valid. Now, at Nethermind, we have a very strong team on formal verification, and you have Julian there, who is the head of formal verification. So for all the technical questions, you can go to Julian. So as I said, we are formally verifying their white paper, and we're doing this in Lean 4. So the code actually mimics and mirrors the white paper, and here you can have, for example, when we show that the balance is, like we will manage to compute that, is monotonic in the first argument. The formalization will be open source, and we are wrapping it up, so it will be available soon. And the white paper will contain references to the formalization. And for the moment, we have around 3.3K of lines of Lean. But now, let's dive a bit into the protocol and see which are the key insights that lead to this nice scaling solution, right? So first of all, if you look at payments, it's true you don't need underlying consensus, and it's necessary to make available on DL1 only a commitment to a set of transactions and to the set of senders who have signed the commitment. And the nice part is that they delegate the DA aspect of the protocol on the user side. So it will be the responsibility of the users to compute the balance of their accounts, to compute to keep track of how much money they spend, how much money they received. Now, the only part in which you have to check that everything is sound is like when you have to do a withdrawal, and you have to compute that from scratch, and I will try to show you how you do this. okay, I think I will just be more efficient and stay here. Hope. Okay, so INTMAX is, as I said, it's a permissionless block building that can be performed in parallel, and it matters only the order in which they will be, the blocks, they will be stored in, on the L1 contract. But note that here, a block is not in the sense of a traditional blockchain, because it doesn't really have to refer to the previous block and so on. It's just a storage on the L1. Now, the block builders, and this is important to understand, is that they don't need to verify the validity of the transaction, so it's stateless. And you don't need to coordinate the builders. You don't need to pick a leader for building a block. So now users, they have 3 actions. They can deposit, they can transfer, and they can withdraw. It's a payment solution. Now, for deposits, an L1 user will just send funds to an L2 address on the rollup contract on the underlying L1, which is going to be Ethereum. And that's stored in the contract storage. Now, the transfer is the interesting piece of the design, and it has 2 phases. So first of all, senders, they have to pick an aggregator. Anyone can be an aggregator. There can be several aggregators. You can, and probably they're gonna use relayers in order to make sure that you don't have a malicious aggregator that can postpone posting your transactions and so on. So let's say we pick an aggregator that we trust, and the senders will start to send a bunch of transactions, meaning that is just a function. Everything is a function. They send, okay, they announce to how many participants, how many tokens they want to send. They send this information to the aggregator. The aggregator creates a Merkle tree, sends the proof of inclusion to the user, to the sender. The sender checks it. Classically, it signs, send it back. The aggregator collects a bunch of valid signatures, aggregate them, and post this information on the L1, right? Now, the other part that is missing is the fact that, so this is just me explaining that you have to have a transaction batch. Now, the other part, the phase 2 of the transfer protocol, is that the senders have to send to each recipient a proof that they actually sent the transaction, right? So each sender will send the Merkle proof that they receive from the aggregator to the recipient that they have in mind, plus with previously proofs that he had at that point. And that's done directly, not via the L1 contract, nothing, right? Now, the withdrawals are quite simple, but there is a twist to it, because in order to withdraw, you have to, even if I want to withdraw my own funds from the rollup, I have to engage first in the transfer protocol, in which I will send the transaction, the amount I want to withdraw. I will send it to an L1 account, and that will be posted on a transfer block. And then I can use the proof that I built and give it to and send it from an L1 account using this proof that I have, send it to the rollup contract, and you do the withdrawal. So, as I said, when you transfer the block, the L1 contract doesn't automatically send the funds to the L1. You have to go through the transfer protocol before, and after that you can do it. You can trigger. But in order to trigger the withdrawal, you have to go through the transfer protocol. Now, what we are formally verifying is their security, well, the safety property, saying that the rollup contract is secure if every withdrawal is fulfilled, it succeeds. So, and we show that, okay, you have to have a trust assumption at the point. So breaking this security result is like either you collapse the hash function or you break the binding property of the underlying authenticated dictionary. Now let's look at the protocol, right? Everyone can be an aggregator. You can be your own aggregator. It may be a bit more expensive for you, But you can do it. So you don't need escape hedges for this protocol. By design, you have it. So everyone can be an aggregator. Therefore, you have censorship resistant, modulo the censorship resistant on the underlying L1. Now, the rollup contract, as I was trying to show in the pictures, manages deposits, transfers, and withdrawals, right? And for each type of the user action, you have 3 different kinds. We call them blocks, but as I said, they don't have to rely to address the previous block and so on. So the contract, the rollup state is just a list of 3 kinds of entities, which can be deposit blocks, transfer blocks, and withdrawals. Now, in order to convince you of the 5 bytes on chain, let's look at the transfer block, which is put on the storage contract, which this is the biggest part. And it actually contains an L1 address of the aggregator, so 20 bytes. This extra data string is used for security reasons, such that you don't have, such that the aggregator will not postpone on posting your block. Then you have the authenticated dictionary, the senders who actually signed it, and an aggregated signature. And if you do the arithmetics, at which I'm very bad, you would obtain this information. But now notice that here, you rely on the size of how many senders you have, not on how many transactions you send. And this comes from 96 because you use BSL signatures. And now you can add compression. I will not go too much into details. You can add compression using a relayer contract. And if you, with the current version of the block size on L1, you get this number, right? And if it will increase, if you will have more space on the L1 blocks, you can reach this point, which is even more than how much Visa transactions you can support at the moment. But now what I want to get into is the magic behind the protocol. Because it seems, okay, but what happens with double spending? Who is doing the verification? A lot of paranoia can come up here, right? So the magic trick is a balance function, which uses a very nice algebraic structure called lattice ordered abelian groups. And you have to use this balance function when users have compute their balances or when the rollup has to do a withdrawal. Now, if you don't know what lattice ordered groups are, it's no problem. There are some algebraic structures that they are used in fuzzy logic, for example. Basically, you have a group such that you can add your tokens, but then you also have a lattice order such that you can compare tokens between them. But it doesn't have to be totally ordered. So you can have uncomparable tokens, and you don't care about that, right? And there are scenarios in which you can think. And then usually in a group, you have positive con and negative con. So obviously the balance of accounts, they always have to live on the positive con of the group. Now, the balance function and why does it work is the fact that you have to split the information between 2 parties. You can have the list, the history of the rollup. You can have all the blocks that have been added to the rollup contract, but without having a proof from a user side, you can't retrieve the state of the accounts, the balances of the accounts. So you need 2 pieces of information. You need a proof that comes from the user, and you need the history of the rollup that is on the L1 contract rollup, right? And a state will just compute this B here are just functions which says, okay, which is how many tokens each account has. And you have to compute this value, right? And in order to do this, you have to split it in 2 parts. First of all, if you have a proof, but you don't know anything about it, you can have partial information there, it can be rubbish, you don't know. And then you have the list of the history, right? So first of all, you have to extract a list of partial transactions from these 2 information. And after this list of transactions, you just apply a state transition function and you compute the balances. This is not optimal, but there is a version in which this can be faster, but I will not go into that here. But the trick is, because you are in a scenario in which you have partial information, the best thing you can do is just compute a lower bound of the balances, actually. And you reason against that, and you make sure that you don't withdraw more than this lower bound. So let's look at an example, right? Here, B0, it's a deposit block, and let's suppose Alice deposits 11 tokens in the rollup. Now, we have two transfer blocks, the yellow one in which Alice sends 7 tokens to Bob, right? So she will go through this transfer protocol, and she will get a proof from the aggregator. Let's call it P1. Now, let's construct a different transfer in which Alice now wants to send 3 tokens to Charles. So she will take a different proof from the aggregator, P2, and Bob will send 7 tokens to an L1 account. He's preparing to do a withdrawal. So that's P3. Now, if you look at their wallets, which are these proofs that they have to keep up with, Alice will merge the two proofs, P1 and P2. Charles will do the same, while Bob will have the P1 received from Alice, and the P3 he receives from the aggregator. And now, if you unfold this one, I know this is quite heavy, you don't have to go through all of it, but what I want to show is that, for example, if Alice will send her wallet to the rollup contract and wants to compute the balances of all accounts against the history that happened, this part here comes from the deposit. This part here comes from the second block in which she sends 7 tokens. And all of this part here comes from the last block in which she showed that, okay, I send 3 tokens to C, but in that block, B appears as well as a sender. But Alice has no information about the proof that Bob received. So we compute this as a partial transaction. We don't know anything what happened. We don't know what Bob did there. Alice doesn't know, and she shouldn't know, right? So we put this as bottom. It's like undefined. We don't know anything. And then when you start to compute the balance function, okay, it does naturally. So this is the value of every account. And okay, for example, here we are expecting that, okay, here after computing the 3 transactions, Alice has 1, Bob has 7, and Charles has 3, right? And this is the source account, which is like the almighty account that is used for the rollup contract. But now, when you try to reason about the partial transactions of which you don't have enough information, and they don't know what Bob did, they will say, okay, I set the account of Bob to 0, and I will reason about this. And depending on how many blocks and how many entanglement you have in your blocks, you will get this part, right? Now, if you look at the information Bob has at this point, and you try to compute the transactions that come up there, so remember Bob had P1 and P3, right? So Bob received 7 tokens from Alice, but then on the second transfer block, Bob has no idea what Alice did at that point, right? So here we have 2 partial transactions on what Alice could have done, right? But Bob knows, like, I want to send to this L1 account 7 tokens. I want to do a withdrawal. And you reason about this. And now the tricky part is, like, how is the double spending happening, right? And know that the withdrawal step ensures that the user cannot double spend the withdrawal to withdraw the same funds twice or to overspend. And this is the very nice part of the mathematical behind the paper. And let's twist a bit the scenario. And let's imagine that at the end, Bob wants to send 9 tokens. Initially, he had just 0. Let's suppose he wants to withdraw 9 tokens, right? He wants to send to an L1 account 9 tokens, which obviously he doesn't have at this moment. And what happens if we go back and we do the same process, we compute the same balances, and at the end, the protocol at this point will just set the account of Bob to 0, but actually, because they use lattice order groups, they are taking the minimum available between the account. All the time, they reason about the lower bound, the minimum of the values that are possible to move. So it will take the infimum between what Bob had in his account and how much he wants to send. And all the double spendings are set like this. The protocol, this magic balance function, will set everything, will not allow you to overspend more than you want. And everything is just doing meets in lattices. And that's very beautiful. And there is a very nice part, because here it allows a partial transaction, right? It withdraws just 7 tokens because it is what he had in the balance, right? The protocol is so general that you can twist it, and playing with the balance function, you can obtain whatever design you want for your protocol. So I invite you to look at the white paper, look at our formalization, and see the beauty of the protocol. Now, obviously what I presented here, and I said from the beginning, for sure this design, the simplified design, lacks privacy, because by the proofs they receive, the users can see the accounts of other users, and that's not okay. But you can use ZK proofs for this, and that's fine, and nothing bad will happen. And then it's not super efficient, because balance proofs are large and are expensive to compute on chain, and they have a very neat way of solving this problem. But I just wanted to go to the lattice orders and show you how you can handle this. Okay, and please reach out to us if you have further questions. Thank you.
Thank you, Denisa.